Right. So Professor Charles Jones and his very famous macroeconomics. He's associate editor of Econometrical Journal, and he published widely in all those top 5 journals. And his research focuses on growth and important topics such as AI and even population growth, right? Related to economic growth. And I think for the topic related to today's talk, he already have a AR Insight paper published, right? So like last year or 2023. Yeah. So so it happens that this last semester I actually include his paper in my reading list. Yeah, because this is AI in general is very hot in econ and other business fields, and this paper apparently is one important question, right? So why don't I give the floor to Professor Charles Jones, and if you have questions, you may use some icon or just raise your hand, and we'll see that. Thank you.
Wonderful, Robin. Thanks very much for the introduction, and it's really a pleasure to be with you all today. I think this topic, artificial intelligence, and I know you guys are having a conference next month on the topic. It is the most important thing going on right now in a world with lots of important things. So I think it's great to have a chance to share some thoughts with you. Okay, so we've all seen the stunning, amazing progress. Hopefully, you guys have been using some of these frontier models, the reasoning models, to help you with math. I use them every day. I think in some ways it's more effective than a first-year PhD student at helping me solve my problems. So I use it all the time to check my work. Writing reports, the deep research models that have been released by a bunch of these companies, protein folding, understanding DNA and new materials. So the progress has been really stunning, and it looks like the progress is only continuing. So, between throwing more computers at the problem and algorithmic improvements, it's estimated that effective compute is rising at about 10x a year, which these scaling laws, especially on the reasoning side, look like they continue. And so I think the prospects for exciting opportunities is really dramatic. And I think there's a chance that great things happen. I'm not going to talk about the great things side of it so much today. Instead, I want to talk about the potentially large risks that might be associated with powerful AI models. And as you know, these risks have been highlighted by the world's experts. So it's not a fringe group talking about the risks. It's Nobel Prize winners like Jeff Hinton and Demis Hassabis, or Sam Altman, Dario Amodei. So these risks are very much at the front and center in a lot of people's minds. And the question I asked when I started thinking about these risks is, what can economic analysis say about these risks and what we should do about them? And so, as Robin mentioned, I've written 2 papers, one that just came out in the AR Insights back in December, and another short paper that I wrote just over the winter break. And I kind of want to talk about that work. Before I dive in, though, let me sort of step back. Sometimes people wonder, what do these catastrophic risks look like? What do the existential risks look like? And I think there are 2 versions that I found helpful to think about. So the first version is kind of the bad actor version of existential risk. So in some sense, it seems very likely that AI is going to be this incredible answer machine. It can answer any question we ask. Maybe any is too strong there, but imagine it doesn't have any agency itself. So it's not going to do any damage, by itself, but it can answer any question we ask, or GPT-6 could answer any question we ask. Well, in the hands of a bad actor, some bad person decides, hey, let me ask GPT-6 to design a COVID virus that's 10 times more lethal and takes 3 weeks to display symptoms, and then releases that into the wild. And so that could do a lot of damage. So I think just sort of the powerful Oracle AI in the hands of a bad actor could do a lot of damage. If you think about nuclear weapons, they were manageable in part because they were so rare. Only, 5 or 10 or however many parties had access to them. And so we could manage those 5 or 10 people. Whereas if everyone has access to this oracular AI, do we really think we can manage 8 billion people who potentially have a red button? Maybe that would be a problem. The second version of existential risk is the sort of more profound, maybe harder to envision version. And I think about that as the alien intelligence version. And so one thing one way it's been put to me that I find helpful is, imagine we found out tonight that astronomers observed a spacecraft on the way to Earth, out by Jupiter or something, on the way to Earth. How would we feel about that? Well, on the one hand, we'd be pretty excited, but maybe 10% chance that this doesn't end well. After all, whenever sort of advanced societies encounter societies that are substantially behind, historically that hasn't often ended well for the people behind. And so I think this is potentially a problem. And there's a CS professor, computer science professor at Berkeley, who's the co-author of one of the top PhD computer science textbooks, Stuart Russell. And I was on a panel with him a couple of months ago, and he put it this way. He said, how do we ensure we have power over entities more powerful than us forever? And I think that's worth pondering as well. So I don't know exactly what the risks are, but these two classes of risks strike me as risks that are worth thinking about and worrying about. Okay, so what I want to do is provide a very quick review of the earlier paper I wrote. I think that sets up the new paper quite nicely. And then I want to talk about how much should we spend to reduce existential risk. I'll try to finish at around 10 minutes before the hour, so we have plenty of time to have some questions. And I think that should not be a problem. It's not a long talk. In the interest of that, let me skip the literature. There are a bunch of interesting papers on AI and economics and catastrophic risks, but let me not review that. Okay, so the 2024 paper was built around a simple thought experiment. And people like Sam Altman or Dario Amodei, Satya Nadella have said things like AGI, powerful AI, may be more important than electricity, but more dangerous than nuclear weapons. Right? And so I thought about the thought experiment in this paper. I called it the Oppenheimer question. So you may remember the Oppenheimer movie, right? When the scientists are getting ready to test the first atomic bomb, right? The Trinity Project. They're getting ready to test it, and some of the physicists say, hey, what's the chance that this atomic bomb creates a chain reaction that it ignites the atmosphere, we can't stop it, and it destroys all life on Earth? And they thought, okay, that's something to be worried about. They went away and did the calculations and came back and said, well, we think the probability is small. Well, small is not zero. And the question is, how small does it have to be before you're willing to take the risk? And so I built a model around that in the context of AI. And the way I set it up, I said, well, let's look at the state of the world where the AI is incredibly powerful. Because if it's not incredibly powerful, then we don't face this trade-off. But if it is incredibly powerful, it might lead to fast growth, but it might also lead to a bad outcome. So the way I set it up, I said, let's assume if nothing goes wrong, then AI accelerates economic growth to 10% per year, just a profound acceleration in economic growth. But in exchange for that 10% per year growth, there's a one-time chance that AI kills everyone on Earth, right? A one-time small chance. So do you take the risk or not? Do you press the button or not? Do you take this risk? And so what risk are you willing to take? A 1% chance, a 10% chance? And what does standard economic analysis imply about this? And so there were kind of 3 findings in that paper, all of which surprised me a little bit. So the first is, I wrote down a model, assume log utility. That's a standard utility function that we all use in economics all the time. It turns out with log utility, you're willing to take a 1 in 3 chance of killing everyone on Earth to accelerate growth to 10% per year. And that was very surprising to me. Macroeconomists are very comfortable with log utility, and there's no way I would take a 1 in 3 chance, I thought, of killing everyone to get that 10% growth. And so, I learned maybe I'm not log utility after all. Okay, so what if you plug in risk aversion of 2 or risk aversion 3? This is the second point. It turns out the problem is very nonlinear in risk aversion, so that with risk aversion of 2, this risk cutoff plummets to just 2%, and with risk aversion of 3, it plummets to 0.5%. So in other words, those seem like much more in the ballpark where I'd have to think about it. But risk aversion 2 or 3, 2% less risk. And the intuition for this is very straightforward. There's diminishing returns to consumption, and the higher is this risk aversion parameter, right? The sharper is the diminishing returns. Utility's bounded with gamma bigger than 1, with risk aversion bigger than 1. And so in some sense, if you think about it, my life in Palo Alto, your life wherever you are, we have a good life. I don't need a 4th flat screen TV or a 3rd iPhone, right? I just need more years of life to enjoy my already high living standards. And so I'm not willing to take a large risk that I might die from the AI just to get a 4th flat screen TV or a 3rd iPhone, right? And so our standard preferences kind of have that built in with gamma equals 2 or gamma 3, and that's why the risk is so small. Okay, so that made a lot of sense to me. The final finding was also surprising. I see this mark here. Let me see if I can figure out how to get rid of it. Delete, erase. I don't know. Oh, clear all drawings. That looked good. I don't know how to do that. Okay, there we go. Okay, so the finding that surprised me a lot is, okay, if AI is powerful enough to accelerate growth to 10% per year, then it's probably also going to do great things with respect to life expectancy. So it might cure cancer, cure heart disease, et cetera, right? So 10% growth is a profound change. So what if at the same time as delivering 10% economic growth, AI also cuts mortality rates in half? That seems plausible. If it's 10% growth, it's probably doing something impressive to mortality. Well, the surprise is, even with gamma equals 3, even with risk aversion 3, even with really sharply diminishing marginal utility, you're still willing to take a very high risk, back up to 25%, to cut mortality rates in half. And the intuition here, which I should have appreciated because I've done related things before, basically, now you're trading off lives versus lives instead of lives versus consumption. You don't have to pass through this diminishing marginal utility. In some sense, all I care about is making sure I don't die. And whether the AI kills me or whether cancer kills me, it's just the total risk that matters, right? And so you're willing to take large risks to cut mortality rates in half, even with risk aversion of 3 or high levels. And this is true even if the social discount rate falls to 0. So one thing I thought I knew was, yeah, if there are these, billions and billions, tens, hundreds of billions of future people, then you might not want to take lots of risks. But it turns out each of those people is just like me. They all want to live for 200 years instead of 90 or 100 years. And so they're each willing to take a very high risk in order to cut mortality rates in half. So the social discount rate turns out not to really affect the problem much at all. Okay, so that was a quick summary of the first paper. This follow-up paper, I came back to this question of how much should we spend? Okay, let's not take the existential risk as given. Maybe it's not 25%. Maybe we can invest and do something about it. And again, at first I didn't write this paper because I thought, okay, if there are tens of billions or hundreds of billions of future people, yeah, you're going to want to spend a lot to prevent existential risk. And I didn't think I had that much to say about that. But as I was thinking about the problem, I realized, in fact, we've faced this exact same question, or at least a version of it, quite recently. And that was during the COVID pandemic. So during the COVID pandemic, we all faced a mortality risk of something averaging something like 0.3%. So, less than 1%, a third of 1%. But we shut down economies to mitigate this risk. In particular, on an average, advanced economies of the world spent something like 4% of GDP just by shutting down the economy to mitigate a pretty small mortality risk. Okay? So from my perspective, the AI risk is plausibly at least this large, and that suggests maybe we should spend at least this much. 4% of US GDP is something like $1 trillion, right? And we're not spending anything like $1 trillion. And so maybe we're massively underinvesting in mitigating this risk. And notice this version of the problem says, just from a selfish perspective, ignore all the future generations. Just from a selfish perspective of us not wanting to die, we might be willing to spend large sums. That was the lesson from the COVID episode. And in fact, you might say, well, was that 4% optimal? No reason to think it was optimal. Lots of people wrote a COVID paper during the pandemic. One of the COVID papers that I wrote with Pete Clino and Bob Hall asked, how much should we be spending to mitigate COVID? And the intuition we got there comes in the following form. So the value of life in the United States, the Department of Transportation, the Environmental Protection Agency, use a value of life of something like $10 million for the average American, okay, say a 40-year-old. Well, if the value of life is $10 million, to completely avoid a mortality risk of 1%, to avoid a 1% chance of dying, you're willing to pay up to 1% of $10 million, which is $100,000. Okay? Notice $100,000 is more than 100% of a year's per capita GDP. So if you thought the existential risk was something like 1% and thought it was spread over 2 decades or something, you might be willing to justify an annual investment of something like 5% of GDP for 20 years, right? So huge sums of money, right? So that 4% based on COVID, we found in our COVID paper was potentially way too little. We could have been willing to spend even more. And so what this suggests is that large investments in mitigation may be worthwhile, even just purely from a selfish perspective, put no value on future generations. Now there's something I skirted over, which is how effective is the mitigation spending? And so we need to write down a model and calibrate it more carefully. But this slide gives you the intuition of what I'm going to find. Okay, so let me show you that model. It's a really simple model. There's a one-time existential risk that occurs with probability delta. There's a one-time investment X you can make to mitigate that risk. So delta decreases if you spend more on mitigation. And there's an exogenous endowment, exogenous income that grows rapidly because of AI, for example. Okay, and then the problem is here in the bottom of the slide. The optimal mitigation problem is choose the amount of mitigation spending X to maximize the present discounted value of utility, where you get U of C today, and then with probability 1 minus delta, you live to get beta times some present discounted value of future utility. And your consumption plus your spending equals your income endowment. And then this V, the present discounted value of future outcomes, is just some exogenous thing. So it's a function of the Y. Just assume you consume Y every period in the future. There's some discount rate. And so we need to figure out, what is this prize that you would lose if the existential risk materialized? And of course, that's related to the value of life. Okay, so if you take the first order condition from that problem, it's a nice intuitive expression. On the one hand, if you spend $1 on consumption, you get U prime of C. On the other hand, if you spend $1 on mitigating risk, well, it reduces the risk by delta prime of X, and you get the price beta times VT plus 1. And so you want to set the marginal benefit equal to the marginal cost of those kinds of spendings. Okay, so that's a nice intuitive first order condition. If you convert it into elasticities, you can get an even more intuitive expression. So let eta be the elasticity of the delta function with respect to X. And let me make it, since delta prime is negative, let me multiply by a negative. So eta is a positive number. So this elasticity, eta of delta with respect to X, tells you how effective is the mitigation spending. And let S be what fraction of your endowment do you want to spend on mitigation. And so just manipulating this first order condition, you get the condition in the box that says S over 1 minus S, and if S is small, that's approximately equal to S, of course, is the product of three terms. So let me go to the end first. This last term, beta Vt plus 1 over U prime of Cc, that's the value of life. Actually, it's the value of life expressed as a ratio to per capita consumption. So if you thought the value of life was $10 million and you thought per capita consumption was $50,000, then this would be a number like 200, right? A lifetime is worth 200 years of per capita consumption, right? Because of diminishing marginal utility, it's worth more than the 50 years or whatever. And then you got to discount it with beta. Okay. And then delta of X, that's the risk to be mitigated, right? So delta times the value of life is kind of that willingness to pay term that I showed you on the previous slide. And then we have to multiply it by the effectiveness of spending, right? And that approximately gives you the optimal share to spend. Well, let's plug in some numbers. I told you that the value of life term is some number around 200, bigger than 180. I'll show you more careful calibration later. What's the risk to be mitigated? I don't know. Seems like it's at least as large as 0.1%. That's only a third as big as COVID, right? So that's small. And how effective is spending? If we increase our spending by 1%, do we reduce the existential risk by 0.1%, not percentage point, but is the elasticity 1 to 10 at least? Yeah, I'll show you some calibrations. That doesn't seem implausible. Well, if you multiply these three numbers together, of course, you get 0.1. Well, 0.1% of 180 is 18%, and then times 0.1 is 1.8%. So even taking very small numbers for the risk and the effectiveness, you get that it's optimal to spend 1.8% of GDP on mitigation. And again, that intuition is gonna shine through when we do the calculation more seriously. Obviously, these things are all endogenous variables that depend on S, and so I've cheated by just plugging in the numbers, but you could do it more carefully, and this conclusion is also gonna come out. Okay, so lots of additional considerations. If you want, you could place value on future generations. That's only going to make it bigger. So you can add, just increase that V. What's the value of the future? Add the value of future generations there, and you can make that much, much larger. And then you might also think of other existential risks. Well, what about getting hit by an asteroid or nuclear war? And then what about competing risks? Well, all these other risks are really tiny, and you can think of them as already being included in the discount factor. And so that's one way to think about how those things show up. Okay, to turn this into a problem we can solve on the computer, I need to assume a functional form. And a functional form that turns out to be very convenient is at the top of this slide. So what does this delta of X function look like? Well, it's the sum of two pieces and lots of terms here. Let me tell you about the terms. Delta 0 is what's the baseline risk if we don't do anything. So that's the 1%, or maybe it's even higher, right? Suppose if we don't do anything, we face a 1% risk. That's the delta 0. This phi parameter is the share of risk that can be eliminated by spending, right? So that gets multiplied by the e to the minus alpha x, right? So imagine you set x equal to infinity. Imagine you spend infinite amounts on mitigation. Well, then the second term becomes 0, and you're left with the first term. So, and you can see, even with infinite spending, you can only reduce the risk, the phi part of the risk, right? 1 minus phi. If phi is a half, you can only get rid of half the risk, right? So that phi tells you what share of risk can mitigation spending eliminate. Maybe not all of it. Alpha is the effectiveness of spending, right? You can see that multiplies the x. And n is the number of people, right? So there's kind of a non-rivalry here. If we all spend, well, we add up the total spending by everyone, right? So there's that effect there. So to calibrate the alpha, I'm going to make one change of variables, which is it turns out to be more useful to define things in terms of this C variable. C is the share of the risk can be eliminated if you spent 100% of GDP for 1 year, right? And it's the share of, consider only the risk that's mitigable, the phi delta 0. What fraction of that would go away if we spent the equivalent of 100% of GDP, right? That's this parameter C. And then cap T is the time of perils. It's the length of a period. So I haven't said this so far. The way I set up the problem, you consume for one period and then you face the risk. Well, maybe one period is 10 years or 5 years or 20 years. I call it the time of peril. How long do we have before we flip the coin to realize the existential risk? And so that's cap T. So I'll calibrate it to 10 years, for example. So, you could spend, okay. All right, so here's an example of the baseline calibration, right? So this existential risk with no mitigation, let me start out with 1%. I'll do some Monte Carlo simulations and let it range from 0 to 2% with a uniform distribution. What fraction of that 1% can be eliminated by spending? I'll set the baseline to be 1/2 and let it be uniform 0, 1. Of the risk that can be eliminated by spending, if you spent a year's worth of GDP on it, how much of it would go away? I'll make that 1/2 also, and let that be uniform, 0 to 1. The value of life I already talked about. When I look at the distribution, I'll let it be 50% of the $10 million, so $5 million, all the way up to $15 million. And you can see, the current value of life is probably an underestimate, because if we got this 10% growth, then lives would be much more valuable, presumably, because we'd have a lot more income in the future. So this is, again, I think, quite conservative. How long is a period? How long is the length of time before we flip the coin? I'll set it to 10 years and look at 5 to 20 years. Risk aversion, I'll set equal to 2. Again, log seems too flat. Make it more curved, or not flat enough, sorry, make it more curved. Discount factor 0.99, again for cap T period, so 0.99 to the T, and make the model purely selfish for now. I'll add this in later, but no value on future generations at all. It's just how much should we selfishly spend to save our own lives? So motivated by the COVID example. Finally, one other intuition. If you plug in that functional form, you get this expression, which again has the value of life times an effectiveness term. And if you linearize things, so if you linearize things appropriately, you get another approximation that I find helpful. And basically, the optimal spending share is approximately equal to this willingness to pay term here, and subtracting now an effectiveness of mitigation term. And I can, on the next slide, I'll give you some intuition for what this looks like. So this is just repeating the same equation. So the beta v over u prime of, now it's u prime of y, because I'm linearizing for a small x, right? And then, okay, so with t equals 10, then a 40-year-old today only has 30 more years remaining. So rather than plugging in the $10 million, I'm going to plug in 75% of the $10 million. So that's going to change the VSL to 120 instead of 180 times a year's consumption. If phi equals 1/2 and delta 0 is 1%, well, then think about this first willingness to pay term. What you're risking is 120 times per capita consumption. There's a 1% chance that you lose it, and mitigation spending can only reduce half of that, right? So you're willing to pay 1% of 120 is 120% of GDP, but you're only willing to pay half of that. So you're willing to pay, ignoring the mitigation, is 60% of GDP. That's really high. For the mitigation term, this C parameter I set equal to 1/2, T was 10, YT is 1, then that subtracts off 20% of GDP. So the approximation would say 60% minus 20%, S equals 40% of GDP. It turns out, I'll show you on the next slide, the linear approximation is not very good if you're supposed to spend 40% of GDP. So the true number is around 15%, but it's still very big. And then second, let me make it smaller. Let me cut the existential risk in half. So rather than 1%, make it 0.5%. Now it turns out the S, right, the 60 becomes a 30, and 30 minus 20 becomes a 10. So now the linear approximation says you're willing to spend 10% of GDP, and that's very close. The correct number, again, I'll show you in this simulation, is 8.3%. Okay, so that's telling you how good this approximation is. For numbers like 10%, it's pretty good. And yeah, even if the existential risk is only 0.5%, just a little worse than COVID, this says you're willing to spend 10 or 8.3% of GDP per year for 10 years. Just an enormous, enormous number. Okay, so using the baseline parameter values, I just told you I got 15%, 16%, 15.8% of GDP. Just an enormous number, you know, kind of too large to be believed in some sense, but you can see why. Again, it's because lives are so valuable. Because lives are so valuable, yeah, you're willing to spend a lot to avoid a 1% risk, and that's just going to come out very robustly. If you make the risk half as large, so the rest of the rows here are robustness, make the risk half as large, then it's 8.3%. That's the 8.3% from the previous slide. If it's twice as large, it's 23. If only 20% of the risk can be eliminated by spending, still you're willing to spend 6% of GDP. If mitigation spending, this C variable, is only 20%, still 7.2% of GDP. What if lives are half as valuable? Still 8.3%. What if the time of perils is 20 years? So you have longer, so you can spend less per year. Still 10 years, 10% of GDP. So for the baseline parameter values, they're always huge numbers. So that's kind of the first finding. Okay. It turns out, I'm going to show you in some Monte Carlo simulations, that it could be optimal not to spend. Maybe you want to spend zero. You're going to see that, you know, in the baseline case with those uniform distributions, about a third of the time you want to spend zero. So I wanted to investigate that. And again, if you look at this first order condition, it kind of makes sense. If the marginal utility of consumption, even when you spend nothing on mitigation, is still bigger than delta prime of zero, then yeah, you don't want to spend anything. So when would that be the case? Well, if you use the functional forms and a little bit of approximation, then you get that you don't want to spend anything. They basically go down here whenever the willingness to pay term times this C times T. Remember, that's the alpha, that's the effectiveness of spending, basically. Whenever the product of those things is less than 1, then this inequality goes the wrong way and you don't want to spend anything. Okay, so plug in some numbers here. If C equals 1/2 and T is 10, and I already told you the willingness to pay was 60%, right? So that was the baseline willingness to pay here. The phi times delta 0 times the beta, that was 60%. If C is 1/2, then you multiply the 60% by 5 because it's for 10 years. And then your left-hand side is 3. So we're way above 1. So that's why you want to spend. But now notice, if phi were 5 times smaller, or C were 5 times smaller, or delta 0 were 5 times smaller, then this inequality would be less than 1, right? If you take the 3 and divide it by 5, then you want to invest 0. And the intuition for that is if the risk is very small, don't invest. Or if there's not much you can do about it, if the spending is just not very effective, then you'd rather have the consumption. Okay, so even though in the baseline case in ladder robustness, I got lots of results that said you want to spend a large amount, if the risk is small or there's not much we can do about it, it could be optimal to spend 0. So that was something I didn't totally expect. And this graph kind of shows you, you know, what do these ISO curves look like? When would you want to spend, you know, more than 0 or less than 0? Let me skip that and show you a different graph instead. So some of these Monte Carlo results. Okay, so for the Monte Carlo results, I do 10 million runs, drawing the parameter values from all those uniform distributions. Okay, and so if you look, I've expressed the uniform distributions here. So what's the baseline risk? What's that delta 0? It's uniform between 0 and 2. So there are going to be some cases where it's very close to 0, and you're not going to want to spend. What share can be eliminated? Uniform 0 to 100%. Again, some of those shares are really small, in which case mitigation spending is not very effective. Or what about the direct effectiveness? what's that C variable? If you spend, what fraction of the mitigable risk can be eliminated? Maybe that's small, or maybe life is not very valuable, right? So if you do the Monte Carlo across these different uniform distributions, this is the set of outcomes you get. And on the x-axis, we have what share of GDP do you want to spend on mitigation? And then we've got the histogram that I smoothed out to make it look like a PDF here. And I've highlighted some key points. So first, notice this 33.1. In a third of the simulations, it's optimal to spend 0. Okay, and that's exactly what I was telling you before. If there's not much you can do about it, or if the risk is really small, don't spend anything. A third of the time, you don't want to spend anything. However, 50% of the time, you'd like to spend 6.4% of GDP or more. All right, so the 50th percentile is at 6.4%. The mean is at 8%. The 75th percentile is up here even higher, et cetera. And so, and 2/3 of the runs, and 2/3 of the time, you want to spend more than 1% of GDP on mitigation. Okay, so you've got this sort of, on the one hand, a third of the time you don't want to spend anything, but life is so valuable that if you do want to spend, you want to spend a lot, and the average of those two things is still a pretty big number. That's what comes out through these simulations. Okay. I did some other things. So make the future. What if we do count future generations? And here I'm saying, imagine we basically double the population. So we count another 8 billion people. So we're not counting a lot of the future, but we're just doubling the weight on the current future. Well, then only 15% of the time do you want to spend 0. And the median is now 16.9%. And then the last thing I do, I remember I set the delta zero distribution to uniform between 0 and 2%. It turns out if you survey, computer scientists or experts in the AI field, AI researchers, their median value for the existential risk is 10%. The experts in this area are very worried. That's why Sam Altman, Demis Hassabis, Jeff, et cetera. Not all of them. Jan LeCun is not so worried, but a lot of them are very worried. And so, what if it's uniform up to 10%? Well, then again, these numbers just get even higher. The amount of time you want to spend 0 is even lower. Maybe there's nothing you can do about the risk, but when you want to spend, it's just huge amounts of money. And this table just summarizes one row I like is actually this last row. What fraction of the simulations would you want to spend at least 1% of GDP? Which again is like 2.5 or $3 trillion. It's a tremendous amount of money, right? And 2/3 or 80 or 85% of the time, you want to be spending this incredibly large amount of money. Why? Life is just incredibly valuable. Right? It's really that simple. Even from a selfish perspective, we might want to spend large amounts. Okay, so let me just conclude with a bit of a broader discussion, stepping out a little bit from the paper, with several questions. So the first set of questions are things I wish I knew the answer to. Right? So in particular, obviously I had to make up a bunch of numbers to do these Monte Carlo simulations, and I put down numbers that I think are justified given the reading of the literature, but it's really, the numbers are all over the place, and so it's hard to know. I tried to be conservative, but how large is this existential risk? Clearly that matters a lot for these calculations. If you thought the risk was 1 in 1,000, well, then that would maybe change how you think about how much we should spend. How much are we currently spending to mitigate AI risk? Each of these AI labs have some people devoted to safety. How much are we spending? What fraction of GDP are we spending? I suspect it's much lower than what comes out of these models, but it would be good to know how much we're spending. And then third, and I don't know how we get this, what evidence is there on the effectiveness of mitigation spending? And again, these labs do safety research, and it does seem to be partially effective. We can do create the MRI for the neural network, for the deep learning, to try to zoom in. You remember Golden Gate Claude, you find these neurons that light up when you ask it a certain question. And, there's been progress in this kind of MRI for the neural networks, for the machine learning models. And so they're trying to see what is it really thinking, and they seem to be making progress. So that's an example of how the mitigation spending could be effective. I think other kinds of, one question I often get when people see these huge numbers is, well, how would we ever, suppose we wanted to spend, $100 billion, which is a tiny number relative to the numbers that come out of the simulation, but still a big number probably relative to what we're spending. What would you spend it on? Well, what fraction of the compute spending is on safety versus on learning to make the models better? I think if you start spending more on safety, you pay people to work on safety rather than paying them to work on other things. I think there's a margin there that could be effective for a while. Another thing to think about is, do we build narrow AI or general AI? Right now, we're racing toward general AI, but if you look at DeepMind, AlphaZero, AlphaFold, the AlphaGo, right? Those were very narrow models that were designed to do one thing really well. And so maybe, for example, based on the two papers that I've presented, maybe focusing on developing cures for diseases. Giving us more consumption, that's not very effective. Giving us cures for diseases, very effective. And maybe you could have a narrow AI that focuses on improving health outcomes, and maybe that would be much safer. So that's an example of how one could, if one wanted to, tilt things in a particular direction that might be very effective. Or, I'll have another thing to say in a second. So this is related to the next bullet point. How should we think about AI competition and race dynamics? So unfortunately, I think you've all seen it. We're engaged in a massive race. All these labs each look at the current environment and say, look, even if I wanted to invest a ton in safety and slow down, it's not going to matter because someone else would win the race. And if we're going to die, we're going to die. And so my actions, my slowing down doesn't really help. So I may as well race. So in the state of the world where someone wins, it's me. And if, and then I get rich, and, if we're going to die, we're going to die. So this has got this sort of, patent race element to it that's just very negative. There's a huge negative externality that these labs are imposing on all of us. How should we think about that is the second big picture question. And then the one answer I have to that is this last set of bullet points. So clearly there's an externality that these labs are imposing on us. What kind of Pigouvian tax could we implement to get them to internalize the externality? And I think one way to think about it is, what if we were to tax GPUs? Right? NVIDIA computer chips are used by everyone around the world to train AI models, right? Tax the GPUs when NVIDIA sells them, maybe tax them enormously, a tenfold tax, right? The price that you pay is 10 times the price of the chip, the price that NVIDIA receives, and use the revenue to fund safety research, right? It seems to me that kind of policy could be very effective. And you might say, well, China's increasingly using their own chips. What about that? Well, again, I think between the US and China, we're back in a world where it's a very small number of actors. China could negotiate, we could have an outside observer enforce that we're both, and testify that we're both taxing our GPUs. China could tax Huawei chips. The US could tax NVIDIA chips. We could use the revenue to fund safety research, and international monitors could, ensure that we're both abiding by the agreement. That does seem like something that's on the table if we should choose to embrace it. And so I do think when I put these two projects together, it seems like on the one hand, life is incredibly valuable, and you want to take that into account with whatever your policies are. So health AI seems really good. Consumption AI may be less valuable. That was the first paper. And then the second paper, we're willing to pay large sums of money, as we demonstrated during the COVID pandemic. We've already demonstrated a willingness to pay 4% of GDP to mitigate a risk that was 1/3 of 1%, shouldn't we be willing to spend an equal amount to mitigate AI existential risk? It seems to be the answer is probably yes. And so then the question is kind of how to do it. So hopefully some of these ideas are useful. All right, that's what I have. It looks like I finished with 10 minutes to spare, so we've got plenty of time for Q&A if anyone has any questions or comments. Thanks very much for your patience and for listening to this somewhat off-the-wall talk. But I do think, as I've thought about AI, I think it's the most important thing happening both on the upside and the downside. And so I hope more people will work on this topic because it seems like it's incredibly timely and important. So thanks very much.
Thank you. So I guess some of our audience indeed have questions or other discussions, right?
Hi, Charles. I have one question. So this is Xijie. Sorry for the light here. Thanks for your insightful talk, and I think I learned a lot from your speech. And one thing, it seems to me that the amount of spending we should have on the mitigation risk is, in some sense, endogenous to the AI progress we can have, right? Like the existential risk gonna be higher if AI improve faster. So in some sense, in your analysis, it seems to me you take the progress as given, study the amount of money we should spend on mitigation risk. But in some sense, these two positive and benefit and cost should be somewhat endogenous. And could you please share some thought on that?
Yeah, no, thanks a lot. I totally agree with you. That was clearer in the first paper. So in the first paper, I kind of had exactly your view, which was, look, maybe the AI is not going to be so powerful, in which case it's not going to give us that much growth and it's not going to kill us. And so let's not worry about it. The state of the world where we have to worry about it being very dangerous is the same state of the world where it's incredibly powerful. So in that first paper, I fed in 10% growth just as a way to make it incredibly powerful. Instead, it comes with a one-time risk. We don't know what the risk is, but what cutoff would you be willing to bear? So that if it's worse than this cutoff, you don't want to take it. If it's less than the cutoff, you do. So that kind of built in this 10% growth. In the second paper, you're right that I was more conservative in that the value of life I was feeding in was our current value of life. So I was pretending that there's no benefit at all from the AI and asking, suppose AI doesn't benefit us at all, but has this risk. How much would we be willing to pay to mitigate it? And so if you fed in that AI is going to be even more powerful, it only raises the amount of spending that you're willing to do. And so since I was already getting big numbers, it felt like from the perspective of being conservative, it made sense not to take a stand on what you're saying. But I agree, you might imagine that the right model has maybe the existential risk and the growth are correlated in some way and they move together. And can you tune how much growth and how much risk do I want? Maybe that would be another model one could write down. I agree, that would be interesting. Thanks.
Okay, thanks. Another question is like, in the reality, how can we tell like whether the economy is spending enough money on the mitigation? Because companies can announce that they spend this amount of money purely on the mitigation, although it's kind of investment plus mitigation, but it's hard to tell this, right?
Yeah, no, I think that's a fair point. You've already seen these labs reneging on their commitments. So OpenAI at some point said they were going to devote 20% of their compute to safety research, and their safety team, all ended up resigning because they didn't devote that 20%. So that does provide an example, by the way, of how you can monitor, right? So it's very clear they weren't giving the 20% because they promised people who came to work for OpenAI explicitly believing they could do safety research, and then they weren't able to and they quit. So I do think things like that would give you a signal, but kind of similarly to the way we did monitoring during the Cold War with nuclear weapons, right? We have these monitors who go in and check that you're doing what you say you're doing, and maybe that would work. But I totally agree. It's a fair question. There's enormous incentives to cheat and lie. And for both parties to really cut back, you need to be sure everyone else is cutting back too. And that requires verification, and that is a hard problem. I completely agree.
Yeah, another point is that, as you just mentioned, maybe another policy we can probably implement is like if you spend X amount of dollar on the AI, maybe 20% of that money should be spent on mitigation risk. This could be an alternative like policy that on one hand like incentivize people's spending on investment to make the AI model better. On the other hand, like control the risk. Yeah, that's
Yep.
my quick thought.
I
Thank
agree.
you.
Thanks
Thank
a
you.
lot. Yeah. No, I see Andrew, you have your hand up.
Yeah, Chad, I really want to congratulate. This is a fantastic paper with great insights. It actually has very profound implications for other areas. I mean, I'm a financial regulator, and the question you ask is really how much insurance should I take, and how much do I need to spend to mitigate that risk, right? And you see this already in financial markets. Regulators are already doing this, except that the innovation in banking is actually pretty limited because they literally control the risk. And then in the stock markets, you see where you don't control the risk and the volatility, actually the payoff is great. But with now new innovation like AI, you can blow up the market, but we just don't know, right? So how much have you now tried to, kind of extend your model to other fields like finance? I mean, I think that would be a great area of exploration.
Yeah, no, that's a great question. So two comments on that. Uh, there's a paper by, maybe a couple of papers by Bob Pendyke and Ian. I'm spacing on Ian's last name. Cited in my research, who've done sort of versions of that. They're finance, at least Ian's a finance economist, so they've done some of the finance stuff. The other thing I'll say though, where I first got interested in this project was a long time ago, 20 years ago, 15 years ago, when I worked with Bob Hall on health spending. So the question we asked in that paper is, how much should we spend on healthcare over time? And a fact you may well know is health spending as a share of GDP is rising in every country in the world, right? If you look today versus, 30 years ago, it's much higher today than it used to be. Why is it? Well, the force we came up with was exactly the force in this model, that as you get richer and richer, risk aversion bigger than one, marginal utility plummets like a rock, utility's bounded. And so the utility I could get from adding more consumption runs into very sharp diminishing returns, and it's more days of life I need to purchase. And so we kind of first used this mechanism to explain why health spending as a share of GDP is rising in so many different countries. And so I think, especially on the trading off lives versus consumption, this force is very active. If you're trading off consumption versus consumption, or dollars in the future versus dollars today, I think finance already has kind of the right framework to think about it. And it's really the lives versus consumption margin that's making a lot of this work. But yeah, it's an excellent question. Thanks. It looks like Long Chen, you have your hand up. Go ahead.
Yes, Chad. This is Long from Luohan Academy. Thanks for the insightful sharing. And I have several questions. Firstly, I've been playing around with the envelope, the formula you're having here. So let's say the value of life is 180 times of your annual income, and let's say the mortality risk is like 1%. And so my first question is, how do you define this effectiveness of spending? So that's how much you reduce that to the fraction of that. Is that what they're saying?
Yeah, that's right. There were two of those parameters. One was sort of saying, look, maybe you think there's a 1% risk, but maybe spending can only reduce half of it and then nothing. So there's a 0.5% risk that you just can't do anything about anyway. So that was that fee parameter. And then the other parameter was, suppose we spent 100% of GDP, 1 year's GDP on mitigation. What fraction of the risk that spending could eliminate would go away? And that's this alpha or this C parameter. So there were two versions, like what fraction can you do anything about? And then of the stuff you could do something about. If you spent 100% of GDP on it for 1 year, how much would go away? So those are the two effectiveness parameters.
Got it. So I think this is kind of still arbitrary at this stage. But in any case, I try to compare this with insurance, and it convinced me that somehow it makes sense, because right now, if you think about the annual mortality rate in the United States, or it's like 0.7 or 0.9% per year, and then we actually spend about 5 to 10% of our income on insurance. So that comes down to, it doesn't matter how arbitrary assume that effectiveness, actually, that's exactly what's going on. For a mortality rate of lower than 1%, the average income, average insurance spending out of GDP is already around 5% a year across the world. So that, I think, somehow makes sense. You can cite that more directly. But then let's move on. I think there are several questions I have to make this more effective. Otherwise, I think you cannot implement this. The first question is, what if say we have kind of the AI insurance, what can we spend on? And you kind of make some assumptions, but I'm going to attack this a little bit. My first challenge is that maybe it's not particularly effective, because I think the thing about AI is that it's not like the disease. It's going to kill part of the people. Probably it's going to kill a lot of people. So we're all dead, like including insurance companies. So what exactly is this mortality? I think you need to have a better, more accurate description of that. Otherwise, you cannot provide a constructive suggestion. So that's my first thing. The second thing is, you talk about the GPU. I'm not sure that's the right way to protect it, because you gave the example in the beginning that let's say there's some bad guy, let's say Hitler. He's going to use the AI to destroy people, but it's not about GPU, right? It's not like you spend so much time to make GPU safe. It's not about that. It's really about the vicious use of the AI. So for that, maybe one alternative suggestion is that maybe in the future we should give GPU license. You can actually track it, and if you find there's some bad guy, it just you can actually control the use of that license. So you cannot use that GPU anymore. Something like that maybe is much less expensive, but it's much more effective dealing with this kind of risk. It's like the moral risk. That's a suggestion. My third challenge for this is that it's very hard for you to implement this at this stage, because right now, actually the risk of any country is that they do not spend enough money on AI, not too much money, because there's a global, like the concern, maybe in the United States is different, but across the world, because of the habit of the economic engines, current models, that actually many countries, because who is spending this? And so that's different, right? Because it's a country or companies. And so a lot of countries, I think they have a problem of spending too little. Maybe the exceptions are United States and China. But other countries is not at the stage of spending several percent of GDP on insurance, on AI insurance. So that's the challenge. I don't have an answer, but I think you need probably to put this into perspective when talk about things like that, to make it more constructive. Maybe sometime down the road, or some kind of schedule, things like that, maybe make it more implementable. The next question is, who's going to spend the money? And is that regulation, or is that something like that? That's related to what's the problem, how can you deal with the problem, and come down to who's going to pay for this. And that, because nobody's going to pay at this stage, I think, for now. People talk about it, but nobody's going to pay for it, because they don't know. It's not unlike insurance. I know if I don't do it, someday I'm going to have the trouble for my health. But AI, people talk about it, but nobody's going to spend on it. So who's going to pay is going to be a problem. Now, my final question is the COVID. Now, COVID is actually controversial nowadays, even in the United States. Now, when we look back, it does kill a lot of people, but what exactly is this? Trump might claim that it's just, I don't know what is he's going to conclude on this. Maybe COVID is just a trick or some kind of, so the lesson of COVID is not as clear as we state. So we want to be a little bit more careful. But in general, thank you very much for stimulate me to think about so many issues.
Yeah, thanks very much for your comments, Long. Those were all appropriate and useful. Maybe just to say one thing about the COVID example. What I find intriguing about the COVID example is, you'll remember we shut down the economy when it was very early and we were very uncertain. We weren't sure what the risk was going to be. We weren't sure how dangerous it was going to be. That feels very much like how we think about AI right now. We're not sure how big the danger is. We're not sure how risky it's going to be. It could be very bad. It might not be very bad. And so I think the parallel, in fact, you don't want to look backward at it. I think you want to look at sort of, March of 2020, that kind of uncertainty we were facing. It feels like we're at that moment with AI. So that was what I found intriguing. But on your other points, I do agree. I think the one other thing I would say is, I think the parallel to nuclear weapons is really helpful. There are these externalities. I mean, when you say countries are spending too little instead of too much, partly it's that we're all racing. And I think from a social standpoint, we're probably racing too fast. And it is just the usual patent race dynamics that, if we're going to die, we're going to die, but I want to win. So we all race, and, and then that ends up with all of us dying. So I do think the negative externalities are very easy to identify. And then it's a question of what's the right tax to internalize the externalities. And that, for me, the nuclear sort of, the way we handle nuclear weapons, especially with China and the US being the two big players in AI, it feels like that is, if our governments got together, and certainly this may be a long shot given how the politics are in the US right now, but it does seem to me it's no one wants to die in any of these countries, and so we want the good outcome, and so working together to ensure the good outcome strikes me as something that is within the feasible set, even if it's politically hard right now. So I hope we'll move closer to that in the future.
Well, my final comment following what you said, let's compare this with a nuclear bomb. My prediction is that the value of your paper will be only seen after the first bomb explodes.
Well, let's hope
but
not,
I think
right?
that's gonna be the way it is with the race, the kind of the remoteness people feel from it, but even people complain about it. But I think we're going to wait for some time to see that. Maybe that's too long, but we'll see.
Yeah. Well, thanks very much for your comments, Long, and thanks to everyone else. Unfortunately, I have to go rush my mother-in-law to the airport, and since she's my mother-in-law, I need to leave right now and make sure I don't make her miss her flight. But I really enjoyed the comments and the questions, and hopefully I get a chance to see you all in person someday. But thanks very much.
Thank you, Chad.
Okay.
Thank you. Thank you, Chad.
Thank you, Chad.